Good
Yeah,
evening.
ma'am, you can start, ma'am.
Okay. Good evening to one and all present here. I welcome you all for the third day of the 1 week online faculty development program on electric vehicle drive system. Today's topic is switched reluctance motor based powertrain for EV applications. I extend my warm welcome to today's speaker, Dr. R. Jayapragash, Sir, Associate Professor, VIT, Chennai. I welcome our HOD sir, Dr. S.VINOD sir, and the faculty members and the participants for this FDP. It's my privilege to introduce sir to the participants. Dr. R. Jayaprakash received the bachelor's degree in electrical engineering from Institution of Engineers India in 2004, and he did his master's degree in power electronics and drive from Anna University in the year 2007. He completed his doctoral degree in electrical engineering from Anna University in 2016. He is currently working as an associate professor at the School of Electrical Engineering, Vellore Institute of Technology, Chennai. His research areas include design of switched reluctance motor, power converters, battery energy storage systems, etc. Welcome you, sir.
Thank you, madam. Thank you very much.
Thank you, sir. Now I hand over the session to sir. Thank you.
Okay. Very good evening to one and all. First of all, I thank the organizers for providing me this opportunity. Thank you once again. Let us start the presentation. Let me switch off the video to avoid network congestions. Right. So today's am I audible to everyone?
Yes, sir. Yes, sir.
Yes. Yes, ma'am.
You are audible.
Right, fine, thank you. So today's presentation is about switched reluctance motor-based powertrain for electric vehicle application. So first of all, let us understand the difference between mechanical powertrain and electrical powertrain, and what is powertrain, what are the requirements of electric motor which is present in a powertrain, and then we'll proceed further. So what is powertrain? Powertrain is a system actually. It is a system consists of many components like axle, differential, shaft drive, engine. Like this, it has got many components which are connected together to form a system called powertrain, and this powertrain is present inside the electric vehicle and which is responsible to propel the system in a forward manner. So if you consider mechanical powertrain, look at this, it has got, as we discussed, right, it has got an axle, differential, and transmission system, gear arrangements, and IC engines, and it occupies more space. It occupies more space. Whereas if we consider electric powertrain, it has got a power converter, inverter, motor, reduction drive. Everything is sealed in a single case. So it's very compact. Your electrical powertrain is very compact, and you can easily accommodate into the system. So that is why we are preferring electrical powertrain compared to mechanical powertrain. Fine. And coming to the electrical powertrain, we know that environmental pollution is one of the major threat nowadays. The complete world, the entire globe is concentrating on the electrification of the conventional gasoline engine. And we may be, there may be a question why, the complete world is concentrating on the electrification of the conventional gasoline engine. Because there are many industries who are, there are many industries which are emitting the harmful gases into the atmospheric air. There are many monoxide substances are added into the atmospheric pollution. But why we have to consider only electrical vehicle? Why we have to promote electrical vehicle? In the sense, the transportation sector is one of the major responsible factor for the contribution of carbon emission. Around 37 percentage of the carbon emission due to the transportation sector. That is why the government is framed many norms and regulations for other industries, and they are promoting the electric vehicle to reduce this environmental pollution. Right. Considering the conventional gasoline engine, whose efficiency is about only 30 to 40 percentage, and it emits more, carbon molecules, and it pollutes the environment. All these things we have studied, and also it requires more space and everything. Coming to the electrical vehicle, If we are using electrical motor and the electrical powertrain, we have to understand the torque speed requirement of an electric motor that we are using in the electric powertrain. So to understand it, we have compared the torque speed characteristics of IC engine with the torque speed characteristics of the ideal powertrain that we are using in the electric vehicle. Consider this red color waveform is the torque waveform and blue color waveform is the power waveform. See, the torque is attaining its maximum value only at a particular speed. For an example, at 2000, consider an IC engine, it develops maximum torque only at 2000 rpm. Whereas if we consider electric vehicle, the major requirement is the electric vehicle has to produce or contribute maximum amount of torque at the starting itself, because it has got a payload, right? So it has to produce maximum torque at the time of starting itself. So this drawback can be eliminated in the electric motor, which is used in the electric powertrain. Look at this, at zero speed itself, if you are using electric motor at zero speed itself or at the starting itself, by using power electronic control technique, we can produce maximum amount of power. We can produce maximum amount of power, right? And this, sorry, maximum amount of torque, and this torque can be maintained constant up to base speed. What is base speed? Base speed is the speed corresponding to the normal voltage and current. Up to this we can maintain constant. The reason is, at low speed levels, machine draws enormous amount of current from the mains, so it has to be limited to the safer value. That can be done by means of PWM technique or by means of chopping technique. So by using PWM technique, we can reduce the current to the safer limit, as well as we can maintain the current constant, flux can be maintained constant, so that torque can be maintained constant up to base speed. Once a machine accelerated to 75% of the rated speed, the EMF induced by the machine will be sufficient enough to provide opposition to the supply voltage, which causes natural reduction of the current. So after that, it is not necessary to provide any additional control circuitry to limit the current to the safer limit or to the safer value. So after base speed, since the machine itself produces sufficient amount of EMF which will provide opposition to the supply voltage, the current will get decreased naturally. In turn, the torque also decreases naturally. So this characteristic is the natural characteristics of the machine. That's when the speed increases, the torque will get decreased. Now we know that P is equal to T omega. P is equal to T omega, right? Now the speed is increasing, the torque is decreasing. So there is an increase in speed and reduction in torque, and so that the power can be maintained constant. So from base speed to critical speed, the power can be maintained constant. So this is called constant power region, which is one of the major requirement for an electrical vehicle present in the electrical powertrain. Because once the machine is accelerated, say your electric vehicle is accelerated, after that for a maximum period of time, it will be in the cruise mode, right? So you can set in an electric vehicle, you can set the speed at a constant value. Even you can remove your foot from the accelerator pedal and you can sit at a safe manner, so that machine runs at a constant mode. Once it reaches the steady state, it runs at a constant speed. So if we are choosing electrical motor for the electrical powertrain which is used in electric vehicle application, the bandwidth of the constant power region should be more. It is one of the major requirement for the electric motor which we are going to use in the electric powertrain. So constant power region should be more. So while choosing the electrical machine or electrical motor, we have to ensure or we have to account all these factors into constraint. So I hope we understood what is a powertrain and the difference between electrical powertrain and mechanical powertrain, and the torque speed characteristics, difference between the torque speed characteristics of IC engine and electric motor which are used in the electric powertrain. Right. So let us discuss requirements of electric motor for e-powertrain. See, we know that conventionally we use DC motors and induction motors, and these are the conventional machines, DC motor and induction motors. And there are many special electrical machines also available in the market. We can make use of it as an electric motor and the electric powertrain, which are permanent magnet synchronous motor, abbreviated as PMSM, permanent magnet brushless DC motor, PMBL DC motor, switched reluctance motor. So these are the various electric motors which are available in the market. We can make use of it according to our requirement, which satisfies the requirement of an electric vehicle. And the requirements of an electric motor are, as we discussed, Your machine should be capable enough to produce maximum torque at the time of starting itself, whose power density should be more. The reason why the power density should be more means the motor which is possessing high power density occupies only very less space. If the power density is more, in the sense per unit volume, the amount of power developed by the machine is more. So we have to choose a machine such that which can give maximum power at a low volume itself. So the power density should be more, energy density should be more, torque density should be more, and the efficiency should be high. Most importantly, the cost should be less. So these are the some of the requirements of electric motor which are used for the electric vehicle applications. So let us discuss one by one. See, if we consider DC motor, right? So we know that DC motor is a parent motor, right? Uh, Even now, if any researcher is introducing speed control technique in the market with respect to the machine whose quality is cross verified with the speed control characteristics of DC motor. Generally, it's a practice, even if you consider vector control or direct torque control, right? Always we will be trying to operate induction machine just like an induction machine, or your characteristics should exhibit the characteristics of DC machine. That way only we will be developing speed control algorithm for an induction motor. So always this DC motor is considered as a parent motor with respect to the speed control technique, because it's very easy to control such a speed machine. We can easily control the speed of a DC motor just by introducing a single rheostat in series with field circuit and armature circuit. We can have a wide variation in speed. We can have a fine variation in speed from 0 to its maximum value. So no doubt about it. But the major drawback is commutation problem, and it requires regular maintenance. So even then, the company called Fiat introduced this DC motor in the electric powertrain in the year 1990 because of these issues, which are dropped in the year 1998. So we know that Tesla is the inventor of induction machine. Now even now Tesla is using induction machine because it's a privilege for them. Very well, we can use induction machine. It is successfully running, but the problem associated with induction motor is complex control strategy, because the machine itself works based on the principle of mutual induction. Even if you make very small change in the stator parameters of an induction motor, right, which immediately affects there will be drastic change in the electrical behavior of the machine, which is not the case in the case of DC motor, because the prominent quality of DC motor is magnetic decoupling. The prominent quality of DC motor is magnetic decoupling. If you make any change in the armature circuit, it will not affect the field circuit. Similarly, if you make any change in the field circuit, it will not affect the armature circuit. That is one of the prominent quality of the DC motor, which makes the speed control easier. That is the reason why we try to operate induction machine just like a DC machine. But but the machine itself works based on the principle of mutual induction. As I said, even if you make slight, for an example, if you are reducing the supply voltage by 2 or 3, or you are reducing the supply voltage by 5, there is a drastic reduction in the torque also, right? Because the torque is directly proportional to square of the supply voltage in the stable region, right? So there will be a reduction in the torque, but the shaft of the machine is always coupled with the load. Whenever you decrease the supply voltage, we may not decrease the load which is coupled with the shaft of the machine. It should not be practiced. So whatever may be the supply voltage variation, your machine should be in a position to supply a sufficient amount of torque to operate the load which is coupled with the shaft of the machine. So it is the control is more complex actually, and it has got a cocking torque also. So the machine should produce. Generally, we use a term called sufficient torque. Sufficient torque is the one, right, which should the machine should produce a torque such that it should overcome the self friction, load friction. If it is an induction motor, it should also overcome the cogging. So torque requirement is more in the case of induction machine. So that is why nowadays most of the companies are not preferring induction machine, rather they are preferring PMBLDC and PMSM machine and SRM machine. So these are the difficulties with the conventional machines. Coming to PMBLDC motor, there are many companies, Ether, using this PMBLDC motor for two-wheeler application. Magendra, Indian-based company. Ether is also Indian-based company. They're using this PMBLDC motor for two-wheeler application. Toyota Prius is using this PMBLDC motor for four-wheeler application. So whether it's a PMBLDC motor or PMSM motor, right, which possesses permanent magnet, the first and foremost thing is the cost of the permanent magnet is more. We are importing permanent magnet from the China, right? And whose cost is more, generally we prefer rare earth material whose cost is it's keep on increasing. You can see from the characteristics. So that is one of the major reason why we are not preferring permanent magnet machines. Moreover, we cannot load the machine to its maximum thermal capacity when we use permanent magnet, because when you load the machine, the current will get increased and the temperature power loss will get increased and the temperature will get increased. The machine, sometimes the permanent magnet material that we are using for the fabrication of the machine may lose its magnetic property. So from this is very clear that the permanent magnet based machines cannot be loaded to its maximum thermal capacity, and due to the cost constraint we cannot fabricate machine for higher power levels. So for an example, here it is stated that in one of the literature it stated that not possible to use it's not like that. Even you fabricate more than 7 kilowatt also. Just I taken from the literature. But these are the difficulties with the permanent magnet machine. So there is a necessity to use a machine which is magnet free and more robust. That is why we preferred to use SRM. Okay, so these are the torque speed characteristics of various machines. So you can see, right? So similar to other machines, your SRM also possesses constant torque region and wide bandwidth of constant power region, and it is magnet free. Because of all these advantages, we started working with SRM. Even this SRM is used by Toyota Prius in the year 2020. They fabricated 60 kilowatt SRM and they used it for four-wheeler applications. Not only for electric vehicle application, there are many industries nowadays started using this SRM. IFB using this washing machine company IFB using this SRM, and for fan applications, for mixer grinder applications, for many applications, many of the companies are started using this SRM as one of the uh, SRM as a electric motor. And as I said, right, this SRM switch reluctance motor as a doubly salient singly excited machine. So before getting into the design of switch reluctance motor, let us understand the overview of switch reluctance motor. This switch reluctance motor is a doubly salient. Hope you might have, everyone might have studied this. Let us have a quick overview and then we'll proceed further. It's a doubly salient singly excited machine. Doubly salient in the sense stator is having inward projected poles. So this is stator and inner portion is the rotor. Stator consists of inward projected pole and rotor consists of outward projected poles. This is said to be saliented structure. So since stator and rotor are saliented, it is said to be doubly salient structure, and it works based on the principle of variable reluctance. It works based on the principle of variable reluctance. See, we all know that for the production of torque, there are only two things. If you consider any electrical machine, whatever whether it's a conventional electrical machine or special electrical machine, right? For the production of torque, only two things are mandatory. Either the machine should possess, or that is, the machine should possess minimum two flux quantities, two flux quantities, minimum two flux quantities, or the machine should possess the variable reluctance property. So if you consider a switch reluctance motor which possesses variable reluctance property, look at this. At the aligned position, the air gap length is very less. So the reluctance is also very less. Reluctance equal to L by mu A, right? When the length of the air gap is less, then the reluctance is also less. Look at this case here, the length of the air gap is more, so reluctance is also more. So the machine is providing variable reluctance which is responsible for the production of torque. For an example, right? Say this is phase 1. Say this is phase 1. It has got diametrically opposite poles. So actually it is a 1 2 3 4 5 6 6 stator poles are there. So the number of phases are equal to 3. It's a 3-phase machine actually. So there will be 3-phase winding. Each and every phase winding is divided into 2 coils, and which are placed on the diametrically opposite poles connected to the DC supply, and this DC supply is switched by means of power electronic converter. Okay, so switch reluctance motor is neither DC machine nor AC machine, rather it is electronically switched machine. Right. So if the A phase is excited, it establishes magnetic field. It establishes magnetic field. Magnetic field consists of more number of magnetic flux lines, which are said to be lines of force. We know the tendency of magnetic flux line. So in an electrical machine, each and every magnetic flux line will act as a separate magnetic circuit, and the magnetic circuit is a closed one. If we consider a permanent magnet, the flux lines will be originating from the north pole and sinking at the south pole outside the magnet. Inside the magnet, it is from south to north. So each and every magnetic flux line can be treated as an individual magnetic circuit. Certainly, it will be completing its path. So here also the magnetic field established by means of exciting this phase A will be completing its path like this. The magnetic flux lines will cross the air gap and complete its path like this. So half of the flux will be completing its path like this, and remaining half of the flux will be completing its path through the left hand side portion of the yoke. Now, the magnetic flux lines having the natural tendency, the flux is analogous to current in an electrical circuit. Flux is analogous to current in an electrical circuit. Current always prefers to flow through the path which offers least resistance. Similarly, flux lines also complete its path which offers minimum reluctance. So the natural tendency of the flux lines is to complete its path which offers the least reluctance, by means of which, right, this rotor pole will get attracted by means of this stator pole, and it will get aligned like this. So so if there is a movement in the forward direction, the torque is developed in the forward direction or in the clockwise direction. So the sequential excite followed by phase 1, if you excite phase 2, again your rotor gets shifted by like this. So the sequential excitation of the phases causes the continuous rotation of the machine. So we are using only concentrated winding in the stator, and the rotor is completely winding free, magnet free. It's a solid structure, nothing else. So the machine is more robust, highly fault tolerant, cooling is very easy, power density is more, torque density is more. So it has got all the benefits of it is meeting all the requirements of an electrical motor which should be used in an electrical powertrain. That is why we consider this machine. Of course, it has got some drawbacks also. Let us discuss in the forthcoming slides. Right. So we understood the construction, working principle, and operation of the reluctance motor. Moving forward, whether it is an electrical, say even if it is a special electrical machine, certainly it should possess the characteristics of the conventional electrical machine. Consider an induction motor. It has got a reversible characteristics. In the sense, the same machine can work as a motor as well as generator. Similarly, if you are using the switched reluctance motor for electrical vehicle application, certainly we have to apply brake. So, implementing regenerative braking mode of operation using an electric motor used in the electric powertrain is very, very important. So your switched reluctance motor also should possess the reversible characteristics. Of course, it possesses reversible characteristics. You can understand from this. See, this is the unaligned position. This is the rotor pole is lying between the two stator poles. This is called the unaligned position. Now, after exciting phase A, the rotor pole is attracted by the stator pole and it has obtained its minimum reluctance position. This is the aligned position. Now, the rotor is moving from unaligned position to aligned position. So, when it is moving from unaligned position to aligned position, reluctance decreasing. Reluctance is inversely proportional to inductance. When the reluctance decreases, inductance will get increased. Look at this profile. This is the inductance profile of a switched reluctance motor. At the unaligned position, reluctance is minimum. At the unaligned position, reluctance is maximum, inductance is maximum, whereas reluctance is minimum. So you'll get a rising inductance region. And the torque equation of a switched reluctance motor is half I square dou L by dou theta. So the torque is directly proportional to square of the current. In the sense, the direction of the current is not going to decide the sign of the torque. The variation of inductance with respect to rotor position is going to decide the sign of the torque. So whether it's a positive current or negative current, whose square will give you the positive value. So it is not going to affect the torque developed by the machine. So it is one of the added factor for the switched reluctance motor. So very well we can use a unipolar converter. Unipolar converter in the sense which allows current to flow through in a single direction, which allows current only in one direction, because it doesn't need any reversal of current through the winding. So very well we can satisfactorily operate the switched reluctance motor with unipolar power converter. I'll tell you what is unipolar power converter. So if you consider this rising inductance region, the rotor position is increasing, inductance is also increasing. So dou L by dou theta is positive. Which means torque is positive. Torque positive is corresponding to motoring mode of operation. Once the rotor leaves the aligned position, this is aligned position. Once the rotor leaves the aligned position, inductance is decreasing because reluctance is increasing. Inductance will get decreased. So here the theta is increasing, but the inductance is decreasing. So dou L by dou theta will become negative. The torque will become negative. So, the same machine can operate as a generator. This is corresponding to generator mode of operation. So the same machine can operate as a generator if we can capture the drooping inductance region and you can excite the phase winding. So this machine also possesses the reversible characteristics like the conventional machines. So very well we can use this switched reluctance motor in the electric vehicle applications. And this is the block diagram of I have given the simple block diagram of electric vehicle. We know that the electric vehicle is classified into broadly classified into three types, like pure electric vehicle or battery electrical vehicle, and then hybrid electric vehicle and plug-in hybrid electric vehicle. Among these three, as a beginner, we can start with pure electric vehicle because if you consider any hybrid electrical vehicle, there are more than 3,000 components. Integrating all these components, understanding its dynamics, developing an algorithm is very difficult. So as a beginner, it is better to start working with the electric vehicle, because once the work is over, we can extend our analysis also. The reason is, right, if you consider hybrid electric vehicle, which cannot be integrated with the grid. Actually, hybrid electric vehicle cannot be integrated with the grid. So nowadays the recent trend is to the many researchers are concentrating on the V2G technology, vehicle to grid and grid to vehicle technology. So the further extension of the work is possible if you work with a pure electric vehicle and plug-in hybrid electric vehicle, where it is possible to integrate with the grid, uh, you know so that we can implement vehicle to grid and grid to vehicle operation. So here we are given the simplest block diagram of an electric vehicle. It has electric vehicle consists of a battery. We know very well it has to be charged, so it needs a charger. This charger can be, it's an onboard charger. It is an onboard charger present inside the vehicle itself. It can be charged using the utility supply at our residence, right? And there is an electric motor which is propelling the machine through wheels. So this motor is one of the major component. This motor, electric motor, present is one of the major component in an electric vehicle, right? So this motor, we are going to use switched reluctance motor in the place of motor. We are going to use the switched reluctance motor, right? There was a complete control circuit is shown here. Right, the switch reluctance motor, as I said, it's neither DC machine nor AC machine. Rather, it is electronically switched machine. It has got many advantages as we discussed. But similar to just like a conventional machine, we cannot easily put this into service. If consider DC machine, if you give DC supply, it will be start rotating. Consider an induction machine, if you give three-phase AC supply, it will be start rotating. But for an as considering an SRM, right, it cannot be easily put into service like conventional electrical machine. It needs very sophisticated, designed power electronic circuitry, and which can be operated only in closed loop. I know we were discussing and in the previous slide that we have to sequentially, we have to excite the phase winding to have a continuous rotation. So which phase winding has to be excited has to be decided by the rotor position information. So this rotor position information is obtained from the switch reluctance motor either by using Hall sensor or IR sensor. Use some standard position sensors which are available in the market, right, and detect the rotor position. Accordingly, we have to excite the phase winding. So this switch reluctance motor can be operated only in a closed loop. So we are detecting the rotor position, right? Rotor position can be converted into speed because omega is equal to d theta by dt. Either you can use a speed sensor or a position sensor. So once if you know the speed information, position information, d theta by dt will give you speed information. So this speed can be compared with the actual speed. Error can be developed using speed regulator. You can develop a current reference which can be compared with the actual current of the machine, and accordingly you can produce control signals to trigger the or to turn on the power electronic device which is present in a power electronic converter. So in this way only we can operate the SRM. So this is what the machine which we are going to now. Our aim is to design this machine. All these things are already existing. We can make use of it. Let us discuss how to design this SRM for an electric vehicle application. That's what our idea, right? So now, we have come across various possibilities of using electrical machines in an electrical train, electrical powertrain. We understood the merits and demerits of various electrical machines, and finally we concluded to making use of SRM for electric powertrain application, right? And the next category is whether we are going to use it for two-wheeler application or three-wheeler or four-wheeler application, right? So we got inspired by means of hand rickshaw. I hope you might have studied an article recently. All the hand rickshaws are banned in the India, and which are all converted into battery operated vehicle. And in the year 2014, central government uh, rule is defined. It's a 16th amendment. So according to the center motor vehicle 16th amendment rule established in the year 2014, right, which gives norms for the special purpose battery operated vehicles, which are replaced the hand rickshaws. According to this, the rule defined e-rickshaw as a special purpose battery operated vehicle having three wheels and intended to provide last mile connectivity for transport of passenger for hire or reward. I'm just reading as it is. This is a rule actually. These vehicles are constructed to carry not more than 4 passengers. Three-wheeler should carry only but nowadays it is not a trend actually. That is different thing. Excluding the driver, 4 passengers excluding the driver, and the net power of its motor should not be not more than 200 watt. So whenever you design e-rickshaw, see to that your power rating of the machine should be lesser than 2000 watt, and the maximum speed of the vehicle should not be more than 25 km per hour. So while fixing the speed, we should limit it to 25 km per hour. So to understand the specifications of electric motor used in the e-rickshaw application, we have done some market survey. Right, there are many electrical companies as well as foreign companies are using electric motor for this e-rickshaw application. Mahindra is an Indian-based company which are using 2 horsepower BLDC motor. Like this, there are many companies. Look at this, all are lesser than 2 horsepower or lesser than 2 kilowatt, lesser than 2 kilowatt. Mostly they prefer BLDC machine, because BLDC fabricating low power BLDC motor is very easy. The cost will get reduced, right? So so we fixed the from we came to know the power rating limitation with from this market survey. We came to know the limitation with the power rating and limitation with the speed. Right, now let us fix the power rating and speed for the SRM based electric powertrain. So to fix the power rating or to calculate the power rating, first we should calculate the tractive force. We all know that what is tractive force. Tractive force is the force required to overcome the friction, or the force required to overcome the resistance due to resistance caused by friction. That's what, same thing. In a conventional electrical machine, we use a term called the sufficient torque. What is sufficient torque? It is a torque required to overcome the self friction and load friction. Similarly, in an electrical vehicle, the electric motor used should produce a sufficient force such that it should overcome the aerodynamic drag force, accelerating force, rolling resistance force, and gradient force. So some of these resistive forces will give you the tractive force. Tractive force is the force required to overcome the total resistance offered by these components. What is aerodynamic drag force? When the machine moves, atmospheric air opposes the motion. So you have to provide, your machine should produce a force such that it should overcome the drag force. And accelerating force, it's a force required for the acceleration. Rolling resistance force, whenever the electric vehicle moves on the road, there exists friction between the road and the wheel. So this friction has to overcome. So the machine, whatever that you are using in an electrical vehicle, should overcome this rolling resistance force. And also gradient force. What is gradient force? Whenever you are operating the electric vehicle in the gradient region, there exists difference in pressure with respect to variation in the altitude. So which causes resistive force, and your tractive force should also overcome this gradient force. Okay, so these are the various resistive forces that has to be accounted to calculate the tractive force. From the tractive force we can find out the power rating of the machine. That is what an idea, right? So to obtain the tractive force, we consider the parameters like speed of the vehicle is considered 25 km per hour, rolling resistance just we have taken from uh, one of the literature, all these things, right? Using these are standard formulae which are existing in all the textbooks and in all the lectures which are available. So we calculated the rolling rolling resistance force, which is mu r mg cos theta. Using these constants we have calculated, which is 26.487 Newton, and then aerodynamic drag force, which is 18.8 Newton. Accelerating force is equal to mass into acceleration. So here you have to concentrate a lot. Actually, this accelerating force influences the power rating of the machine like anything, because generally we calculated the accelerating force like mass into acceleration. Mass is we are considered 180 kilogram is the mass. Acceleration is velocity by time. So 25 the speed of the vehicle is 25 kilometer per hour. From the market survey, we understood that speed of an e-rickshaw should be 25 kilometer per hour. Converting this into meter per second, you will get 6.944 meter per second actually. So 180 kg velocity is 944 Newton, sorry, meter per second. Now that this is time, actually the time generally while designing electric motor for electric vehicle application, we consider this time. This time is the time required for an electric motor to reach 60% of the top speed. This time should be, it's a thumb rule I'm saying. Generally while designing electric motor for electric powertrain application, this time should be considered as 60% of the top speed. 50% of the top speed, 60%, say the speed is top speed is 100 kilometer per hour, then this time should be time taken by the machine to reach 60 kilometer per hour. So this is the acceleration time. This is the acceleration time. For the sake of ease of analysis, right now I'm going to consider t is equal to 10 seconds. Right now I'm going to consider t is equal to 10 seconds. If 10 seconds, then 6.994 divided by 10 will get 0.69. 0.69. So 0.69 multiplied with 180, you'll get the 125 Newton. You'll get 125 Newton. Right. Since it's a e-rickshaw application, e-rickshaw is going to cover only very small distance, say for 1 kilometer or 2 kilometer. For this, purpose only, we will be using the e-rickshaw, not for long travel. So if that is the case, we can neglect this gradient force. For the sake of ease of analysis, I neglected this. I consider theta is equal to 0, sine 0 is equal to 0. So the gradient force will become 0. Now summing up the remaining quantities, you will get, 26.487 plus 18.8 plus 125 will give you 170 Newton. Put together, the tractive force is 170 Newton. So the tractive force required for, okay, I'm just giving approximate thing. Okay, so you can follow the same procedure. So the tractive force required for the e-rickshaw application is 170 Newton. So to calculate the power requirement for an electric motor for traction, this tractive force should be multiplied with velocity. So 170 should be multiplied with velocity. Velocity we calculated already, it is 6.944. It will become 1 kilowatt. Actually you will get approximately you will get actually you will get 1182.47 watts. I have approximated to 1 kilowatt. I have approximated to 1 kilowatt. Since the power density of SRM is more, we can achieve the same job with 1 kilowatt motor itself. That is what an idea. So we fix the power rating as 1 kilowatt. Right. Next one is, so we calculated the tractive force, and from the tractive force we calculated the power requirement of an electric motor, and followed by we have to calculate the tractive torque required at the time of starting as well as in the cruise mode. So at the time of starting, as we discussed, right, if you consider IC engine, which is not having the capability to produce maximum torque at the time of starting itself, only after the acceleration, the IC engine can produce sufficient amount of torque. Whereas if you use electric motor, since it is possible for us to produce maximum amount of torque at the starting itself, right? So the tractive torque should be calculated while starting. So for that, we are going to multiply the tractive with respect to the wheel radius. Wheel radius we have calculated as 10 inches actually. This is an existing data. 10 inch we have considered as 10 inches. Multiplying with meters, you'll get 35.36 Newton meter. So this is the torque required by the machine at the time of starting to overcome the resistive forces, okay, and the payload. So this is what the starting torque required by the machine. It is 35.36 Newton meter. right? For this we calculated the tractive force, which is the sum of all the components, and during running, during continuous running, we it is not necessary to produce the same amount of torque. Okay, in that case the radius of the rim is multiplied with the rolling resistance, aerodynamic drag, and the gradient along. Gradient already we considered. We haven't considered the acceleration, FACC. Acceleration force we haven't considered because the machine is already accelerated using the torque 35.36 Newton meter, and then it has attained its steady state. After attaining the steady state, not necessary to consider the accelerating force. You can consider only aerodynamic drag force and rolling resistance force to calculate the continuous torque required by an electric motor, which are used in the electric powertrain application. So it is the running torque is 9.36 Newton meter. Okay. So considering this, the motor power rating is fixed at 1 kilowatt. So now we fix the power rating of the machine, speed of the machine, torque, and all those things. Now we have to design the machine. So this is also a design procedure actually. So now the design specifications we are going to fix. The power rating of the machine is 1 kilowatt. Rated speed I fixed as to 3000 RPM actually. I'll tell you why it is 3000 RPM. Rated current is 20.83. Supply voltage is 48. As I said, the SRM is, it's a special electrical machine. It's neither DC machine nor AC machine, but it is electronically switched machine to switch the current, and to inject electric pulse into the stator circuit of a stepper motor. It needs a power electronic converter. Generally, we use asymmetric off-bridge converter actually, which is supplied by constant DC voltage, which is supplied by constant DC voltage of magnet, because this is the standard voltage rating which is available in the market. So we consider 68, even you can go for 60 voltage battery, not an issue. Accordingly, the current will get decreased. So 1000 divided by 48, I is equal to P by V, I is equal to P by V. So 1000 divided by 48, you will get 20.833 ampere. Rated speed I fixed at 3000 RPM. Okay, so I'll tell you why. The continuous torque we got it from the previous calculation, which is 3.2 Newton meter. So by considering all these parameters, we obtained all these are the electrical specifications of the machine. These are the electrical specifications of the machine. Using these electrical specifications, we obtained the mechanical specifications of the machine by using the standard procedure given in the R. Krishnan book. There is a book, a design analysis of switched reluctance motor by Professor R. Krishnan. We just used it and we obtained the rotor polar stator. All the mechanical parameters are obtained. Outer diameter, shaft diameter, pole height, stack length. All these parameters are obtained by using the standard procedure available in a textbook. So to understand those, the mechanical parameters, just we are given this diagram. This is the stator pole height, this is the stator pole thickness, and this is the stator coil, and this is stator polar beta S. Beta S is the stator polar. It's the angular width of the stator pole, and this is beta R, rotor polar. That is the angular width of the rotor pole. This is the shaft diameter, and this is the rotor core length. This is the rotor pole height, and this is the air gap thickness. Just to understand the technical terminologies we use, we have given this cut section of SRM. And after obtaining all these parameters, we have to find out the frame. For frame, the standard frames are available in the market. Standard frames are available in the market. We can make use of it. IEC has given the motor frame chart. You can refer it. IEC, International Electrotechnical Commission, has introduced the motor frame chart, right? So you can select any frame. You can fit it into IEC 71 or IEC 80 or IEC 63. For us, the shaft diameter is 14. For us, the shaft diameter is 14 mm. So actually this shaft time, all these things has to be fine-tuned actually, because theoretically we'll be calculating something, and practically, for an example, if you consider shaft diameter is equal to 14 mm, at both ends, both at the front end and rear end of the machine, it has to be fixed with the bearing. So what is the inner bore radius of the bearing which is available in the market, we have to understand. Accordingly, we have to decide the shaft diameter. So that is also one of the major factor. So for this, for us, we have obtained 14 mm. So we decided to use this IEC 71 frame. So we fixed, all the parameters. We followed this IEC 71. Accordingly, we have, fine-tuned all the factors. So once if we fix the frame size, in the same frame size, So that is the beauty actually. We have to find, it's not a single step solution. Designing the machine is not a single step solution actually. You have to find, because in the same frame size, we have chosen IEC 71 frame size, but now in the same frame size it is also possible to accommodate in even 1.8 kilowatt motor. So as an electrical engineer, it is our responsibility to come out with the number of turns, conductor size, spacing, insulation. The many factors has to be considered to account to design a machine. Designing a machine, certainly every electrical engineer can understand it is not an easy task. The many factors has to be considered. So still we are fine tuning. So okay, fine. So for these things, for these geometry specifications, right, we have developed a finite element analysis model. And before that, I just forgot to tell you one thing. Here we have calculated accelerating force, right, FACC, which is a product of mass into acceleration. Here, for the sake of ease of analysis, I consider 10 seconds. See, now just think of it. 10 seconds is more actually. We should not consider 10 seconds. For an example, for the ease of analysis purpose, we are doing this. Suppose if you are reducing the acceleration time, suppose if you want to, if you need faster response at the time, within a quicker interval of time, if you want to accelerate the machine to 60% of the top speed, say for an example this racing bike and all those things, it needs more very lesser acceleration time. So if I'm reducing this 10 seconds by 2 seconds, the power rating and the F phase, this accelerating force will get increased. When the accelerating force increases, then the power rating also increases. So that's what I'm saying. This calculating the accelerating force is very important. So the time required for acceleration also decides the power rating of the machine, which directly influences the power rating of the machine. So by keeping this in mind, we have to determine the power rating of the machine, which is most important. So we can treat it as one of the operating variable actually. So for these, geometrical parameters, we have developed the finite element model of the machine using the electromagnetic tool called magnet. You may have this, at your institution. You can practice it. Electromagnetic tool called magnet. We developed the machine. So this is rotor, stator. It's provided with the coils. Say this is a phase winding. It's a 4-phase winding. So as I said, right, the each and every winding is divided into 2 coil groups. This is coil A and this is coil B. Coil A and coil B are connected such that the EMF or the flux produced by the individual coils are additive in nature. So accordingly, you have to excite the phase winding, right? And in the case of finite element analysis, I hope we all know this finite element analysis, which works based on the principle of numerical integration. The software is developed based on the numerical integration technique, where the complete problem region is segmented or discretized into several smaller problem regions. Look at this is the discretized pattern, where the complete problem solution is discretized into several small portions. So now your software will be treating the individual, a discretized portion as an individual problem. It will be solving it at the back end using iterative solution like Newton-Raphson, Runge-Kutta, something like that. Finally, which are all summed together to obtain the total solution. So this is the mesh pattern at the aligned position, where the rotor pole and stator pole are aligned together. This is the mesh pattern at the unaligned position, where the rotor pole is lying between the 2 stator poles. And after exciting the machine, we excited this phase actually to obtain the steady state characteristics. To obtain the steady state characteristics, you can excite any one of the phase, that is sufficient. To obtain the static characteristics, you can excite any one of the phase, it is sufficient. We excited A phase winding, right? And simulated the FEM model with the various magnitude of current. You can see that the flux is established, right? The total flux is divided into 2 components. Half of the flux is completing its path through upper part of the outer yoke, and the remaining part of the flux is completing its path through lower portion of the stator yoke. So if you see, each and every flux line is a closed one. Each and every flux line is a closed one, which is having the tendency to complete its path, which is offering the lowest reluctance. So aligned position offers lowest reluctance. So your magnetic flux lines are completing its path through this lowest reluctance region. And you can see that in the case of aligned position, the flux lines are crowded. You can find crowding of flux lines at the pole tips, right? Because of this crowding of flux lines, your pole may get saturated. As far as switch reluctance motor is considered, part saturation. Part saturation in the sense some part of the machine, saturation of a few portion of the machine is said to be part saturation, which causes increase in the energy transfer, So in SRM, you can forcibly introduce the saturation. It is not going to affect, rather it will increase the energy transfer ratio. Hope you might have studied all these things in a theory. Okay, right. So there is the reason for this saturation of pole is crowding of flux lines. When the same machine is tested at the unaligned position, see at the if you are simulating the machine within the aligned position, you can get the parameters like aligned inductance. You can get the aligned inductance, and you can plot the magnetic characteristics. That is why we are doing all these things. In the next slide, I can show you. So this is the flux pattern of the machine at the unaligned position. At the unaligned position, here there is no saturation because the complete flux is divided. In the yoke also it is divided. In the rotor pole core also it is divided into two components because it is an unaligned position. Half of the flux will be completing its path like this. Remaining half of the flux will be completing its path through another portion of the rotor core. So the pole will not get saturated actually. So look at this. So this discussion is very useful to understand this magnetic characteristics called the flux linkage characteristic. Look at this. The bottommost curve is the magnetic characteristics corresponding to the unaligned position. See, the curve is linear. Curve is linear. It is not saturated. Okay. For the increase in current, the flux linkage is also increasing. So this is the flux linkage characteristics at the unaligned position. The curve is linear because the material is not saturated. Core material is not saturated. Right. So when you keep on move the rotor at the aligned position, we found that due to the crowding of flux lines, the core material got saturated, right? Saturation, because of the saturation, right, you will get a characteristic like this. The area between the aligned position and unaligned position will give you the energy transfer actually. Okay. So if both the curves are linear, the area between these two curves is very less. If the curve is non-linear like this, the area between this curve will be more, so work done will be more. That is the reason why we allow part saturation. In the case of SRM. So using this electromagnetic tool magnet, right, and by developing the model, we obtain the magnetic characteristics and we obtain the flux linkage characteristics. Once if you know the flux linkage, you can plot the inductance profile. You cannot get the inductance profile from the magnet. You can get it from some other software, but magnet you cannot get it. But you can easily find out inductance. Inductance is equal to flux linkage by current. So you know the flux linkage as well as you know the current. Dividing one by another, you will get the inductance. So using Excel, you can plot the inductance characteristics. Look at this. This is the inductance characteristics. Inductance equal to flux linkage by current. That is, when the current increases, inductance will get decreased. So the bottommost curve is corresponding to large value of current. Actually. And look at this at the unaligned position. Whatever may be the variation in the current, unaligned inductance never changes. Because inductance is maximum. Right, there is no core saturation. So generally, unaligned inductance is treated as a constant one, and other intermediate regions, it will be changing according to the current value. So when the rotor completes one revolution, if you can say SRM, when the rotor completes one revolution, it undergoes NR cycle. NR in the sense, NR is number of rotor poles. It undergoes NR cycles of inductance variation. So you'll get 4 cycles of inductance variation. And this is the torque characteristics which we obtained from the static characteristics of SRM. As I said, we have given this graph to understand that the machine possesses the reversible characteristics, right? So when the rotor moves from unaligned position to the aligned position, right, reluctance will get decreased. Right? Reluctance will get decreased, and the inductance will get increased. Dou L by dou theta is positive, and the torque is also positive. So so you have to capture the region at which the rotor moves from unaligned position to the aligned position. And if you excite the power electronic devices which is present in a converter, you can produce the positive torque. So this is corresponding to motoring mode of operation. Whenever the rotor leaves the aligned position, dou L by dou theta is negative, and the machine produces negative torque. So if you can capture this portion and excite the phase winding at this region, that is in the drooping inductance region, it can operate as a generator. So using SRM, in the electric vehicle, you can implement the motoring mode of operation as well as the regenerative braking mode of operation. That is what an idea behind this, torque speed characteristics. So far, we have done the static characteristics and we obtained the characteristics of the machine, right? We obtained the aligned inductance, unaligned inductance, flux linkage at various rotor position and various current, right? And the torque, maximum torque contributed by the machine, that is static torque required, all those things we calculated. Now we can do transient analysis, that is you can make the machine to rotate and then you can find out the transient characteristics. So this is the circuit which we developed in the same electromagnetic tool called magnet. See, as I said, each and every phase winding is divided into two coils which are connected in series, and and there actually this is asymmetrical off bridge converter. If these two switches are close, the current will be flowing through the phase winding. The current will be flowing through the phase winding, and the inductor will get magnetized, right? And it produces a magnetic field, which causes rotor pole will get attracted by stator pole, and the torque will be produced. Okay. After that, if you want to have a continuous rotation followed by A phase, you have to excite the B phase. So before exciting the B phase, this A phase should be completely magnetized, because say if the flux contributed by the machine is 100%, out of this 100%, only say for an example, I'm saying 90% of the flux established by the machine is utilized for the energy conversion process. The remaining 10% will remain in the field itself. It has to be demagnetized. It has to be demagnetized completely, and then you have to excite the incoming phase. So it is necessary to provide freewheeling path for the current, okay, so that we can demagnetize the energy which is remain in the winding, so that you can excite the next phase winding to avoid the mutual inductance, to avoid the issues related to mutual inductance. So once if you, to demagnetize, just turn off these switches, turn off these switches. Probably here it will be very clear. See, when these two switches are turned on, your phase winding will get excited and it produces force and machine produces rotation. After this, to excite the next phase winding, before exciting the next phase winding, this has to be demagnetized. To demagnetize, right, these two switches should be turned off. Once if you turn off, right, the magnetic field will get collapsed and these two diodes will get forward bias, and the energy which is remain in the field will be pumped back to the source, in this manner. So if you use asymmetrical off-bridge converter, you can utilize the energy which is remain in the phase winding in a productive manner. That is what the prominent quality of asymmetrical off-bridge converter. There are n number of power converters are available to excite the stator phase of the switch reluctance motor. Literature says that asymmetrical off-bridge converter is the best converter. You can go through it. So we use asymmetrical off-bridge converter because it satisfies all the requirement. The fault tolerant capability is there, right? And then extracting the energy which has not been converted into mechanical work possible, and the pumping back to the source is possible, freewheeling is possible, demagnetization is possible. That is why we are using this converter. Okay. So as I said, in the transient analysis, you can run the machine. We run the machine at 3000 rpm and we captured all the phase current. It's a 4-phase machine. You can find 4 different colors of current, right? So these are the phase currents, these are the inductance profile, torque, voltage. We supplied 48 voltage, and look at this, the torque is around if you find out the average value, it will become 3.2. Actually, it will become 3.2 actually. Say it is 3 newton meter, say it is 3 newton meter, okay. But we, while calculating the torque required at the time of running, we have calculated as 9. Actually, we have calculated as 9, but this machine is giving only 3 newton meter, 3 newton meter. So it is necessary to use a gear arrangement. It is necessary to use the gear arrangement. Using gear arrangement, increase the torque by 3 times. Increase in torque by 3 times causes reduction of speed by 3 times. So we fix 3000 rpm, it will get reduced to 1000. Okay, if necessary, we can see, we have to properly, I'm just saying approximately, you can properly choose the gear ratio. Okay, it is most important. right? Because already we are passing 20 amperes of current through the winding. For that, for this itself it needs a large conductor area. To produce without gear, if you want to produce 9 Newton meter, then it needs large conductor diameter, which cannot be accommodated in the space available in the stator circuit. So by avoiding all these complexities, we use this. Now, most importantly, we calculated the radial force. We calculated the radial force. It is maximum. It is around 26.12 Newton. 26.12 Newton. I hope you all know this theory. So this is one of the challenge with respect to SRM, right? The challenges of SRM are torque ripple and vibration. So not only SRM, all the machine, the force produced by all the machine can be divided into two components. One is the tangential force, another one is the radial force. Tangential force is responsible for the torque production, whose variation will give you torque ripple. And the radial force is responsible for the vibration of the machine. So while designing the machine, it is our responsibility to reduce the radial force contribution of the machine, because radial force is the responsible factor for the vibration of the machine. So how to reduce the radial force? How to reduce the radial force? Okay, that is the next question. So radial force can be reduced either by means of structural modification or by control strategy based modification. Since we are very interested in machine design, we preferred structural modification. By doing structural modification, it is possible to reduce the radial force contributed by the machine. In turn, the vibration can be reduced. That's what an idea. So it is just as we introduced rectangular windows. We introduced rectangular windows in the rotor core actually. See, it may be looking very simple. It may be looking very simple, right? Maybe introducing windows is very simple. It is not like that. Even a 1 degree change in the geometrical, 1 degree change in the geometrical specification. 1 minute, Manish. 1 degree change in the geometrical parameter causes drastic change in the electrical behavior of the machine. For an example, let me tell you. See, we use pole shoes, right? We use pole shoes. Generally, the pole shoes are curved like this. Okay. The reason for curvature is to distribute the flux evenly in the air gap, as well as your alternator can produce a sinusoidal waveform like this. Instead, if I introduce a flat portion like this, if I introduce a very small flat region, you don't get a sinusoidal waveform, rather you will get the flat topped waveform. It looks like sinusoidal, but it is highly distorted sinusoidal component. If this component is injected into the machine, it is so obvious your machine will produce lot of torque ripple, leads to acoustic noise and vibration. Okay, so from this is very clear that even a very minute change in the structure of the machine causes drastic change in the electrical behavior of the machine. As an electrical engineer, we should understand. Okay, right. So now coming back to introducing window, the reason why we introduce windows, the concept is, we know that the speed of the sound wave is larger or higher in solids. The physics we should understand, right? The speed of the sound waves is higher in solids than liquids and air. Okay, and the speed of the sound wave is lesser, right? When it passes through the air. So we thought of introducing windows like this. So when the sound wave propagates through air, right, whose speed will get reduced. When the speed of the sound wave which is propagating through the structure of the machine reduces, the vibration can be reduced. That's what an idea. But it's not very easy to fix a window. The core should not be get saturated, right? So we have to formulate the constraints. So we have formulated our own constraints. These are the constraints we have formulated. So without affect, because the introducing window should not affect the static torque, should not affect the running torque, should produce sufficient amount of MMF. All there should not be more ripple. All these factors should not be saturated. All these factors are considered into account, and we developed our own criteria. Accordingly, the windows are placed. After placing windows, again we simulated the model in the magnet environment. We obtained the flux linkage characteristics, inductance characteristics. You look at character. See the when we pass the rated current through the phase winding 20 ampere. We obtained maximum torque of 12 Newton meter. So at the time of starting, this is the static characteristic. This is the static characteristics. At the time of starting, it needs 36 Newton meter. According to our calculation, at the time of starting, it needs 36 Newton meter. So if you use gear, we have to use a gear arrangement to increase the torque, so that the torque can be increased by 3 times. Torque can be increased by 3 times. If the torque is increased by 3 times, the speed will get reduced by 3 times, so that the power can be maintained constant. The gear is very similar to transformer action. Okay, so power can be maintained constant. That's what an idea. So using gear, we can increase it to 36, and I can run the machine. And also for the same machine, we have done transient analysis. Transient analysis, look at this, the average torque is around 3 Newton meter, multiplied with 3, you'll get 9 Newton meter, which is the continuous torque requirement of the machine. Which is the continuous torque requirement of the machine. This is the voltage, supply voltage, current, inductance, all those things are plotted. And also, right, look at this, without a window, we found that the radial force, which is 26.12 Newton, which causes more vibration. Even we have done model analysis in the Maxwell ANSYS software. We found that there is more deformation. There is more deformation in the structure of the machine. So by means of this, we reduce the radial force. Almost, it is almost is very less, actually, very less. And after this, we have done model analysis using Maxwell ANSYS. We found that the deformation is very less, very less. So in this way, you can reduce the radial force. This is just an example, right? Because as I said, a radial force is one of the major factor for the vibration of the machine. It has to be reduced. It can be reduced either by means of geometrical modification or by means of control-based technique. Okay, this control-based technique, it's more things are there to consider. So that's why I just, since we are very interested in machine, we thought of doing geometry modification, right? And we found that there is a drastic reduction in the radial force, and we have done many more modification also. Due to lack of time, I'm just stopping with this. And then we have calculated the, see now actually it's a flow. I hope you all know very well. You're all researchers, right? When we want to implement something, right, first we have to do analytical calculation. We have to touch pen, we have to write it in a notebook, because we cannot go into the machine to analyze the performance of the machine. So for every, as an electrical engineer, we should be in a position to give electrical equivalent, and mathematics is a tool for an electrical engineer. Using that, we have to calculate all the parameters. After finding out all the parameters, it has to be cross verified with the simulation result that we have done it. After that, we have to go for the implementation phase. As far as SRM is concerned, this aligned inductance and unaligned inductance is very important. So whatever the aligned inductance and unaligned inductance which we got from the magnet software is validated by means of this experimental setup. This is the machine which I developed already for my research work. Look at this machine. Actually, it is a 1 horsepower machine. It is a 1 horsepower machine. If you may be wondering, the size of this 1 horsepower machine is, it's very tiny, actually, whose size is around 1/4 of the quarter horsepower induction motor that we are using in our residence for pumping water from sump to the tank, which is placed at an elevated level. So it's very tiny, because whose power density is enormously high. You can easily accommodate this machine. That's what the beauty of this machine. And to calculate the inductance, I just excited, because I need aligned inductance. So aligned and unaligned inductance. So I, for getting the aligned inductance, I just excited. Look at this. See, we designed a machine with independent phase control. Like this, you will get 8 wires. It's a 4-phase machine. Each and every winding has got 2 wires. There will be 8 wires. Remaining 6 wires are wound and kept it on the machine. And I use only 2 wires, and I excited. This is what the DC supply, which produces DC voltage, and it is switched by means of this MOSFET based driver. And let me tell you how to calculate this inductance in practice. This is what the circuit we used, actually. So this is the equivalent circuit of the circuit machine, experimental setup. This is what the phase winding, actually. The inductance of the phase winding, the resistance of phase winding is lumped out, right? This is the MOSFET, IR 540 MOSFET, and it has to be turned on. For that, we use a driver. You know what is driver, right? A driver is used to provide electrical isolation between high power electronic circuit and low power electronic circuit. The PWM signals are generated using microcontroller. We use PIC microcontroller, and generated PWM signal, right? And say if it is a low power version microcontroller, it will be operating at 3.3 voltage. If it is a regular microcontroller, it is operated at 5 voltage. So in turn, See, if the VCC itself 3.3 voltage, the control signal which you are deriving from the microcontroller also having the range of 3.3 voltage, which is not sufficient enough to trigger the power device which is present in a power electronic circuit. So it has to be magnified, it has to be amplified. So we use a driver. So driver, the one of the major role done by the driver is it amplifies the control signal to the level required to turn on the device which is present in a power electronic converter. So we used MCT2E, it's an optocoupler. Not only MCT2E, you can use PC817, PC817 according to the frequency. This PC817 can drive up to 30 kilohertz for I think I'm correct. For more than this, you can go for TLP 250 to operate the power converter at the higher frequency level. Okay, so it is accordingly you can decide. It's up to you, right? So we use this. So this driver magnifies the control signal as well as it provides electrical isolation between the low power circuit and high power circuit. So it is magnified and supplied. So once the MOSFET is turned on, the phase winding will get excited. Phase winding will get excited. Once it is excited, it will be pulling the rotor. It will be pulling the rotor to get aligned with the stator pole. It will be pulling the rotor pole to get aligned with the stator pole, and the machine will reach its aligned position. That is what an idea. If you excite any one of the phase winding, rotor pole will get aligned with the stator pole, right? Okay, and also it is mandatory to provide freewheeling path. Once if you turn off, right, the energy which is in the phase winding will get discharged through the internal resistance of this freewheeling diode and the internal resistance of the winding. Now the freewheeling diode will get forward bias and the energy remain in the winding will get dissipated like this in the form of heat. It will get dissipated. Here we don't utilize it properly. I know very well we are not utilizing it properly because our aim is to find out only aligned inductance. I am not using it the circuit for the regular operation. So that is why I used this simple freewheeling circuit. After doing this, the concept is we know that from the transient behavior of the RL circuit, we understood that your RL circuit takes 5 times the tau. Tau is the electrical time constant, which is the ratio between inductance and resistance of the winding. So if you can say any RL network, it needs 5 times the electrical time constant to reach its steady state. So by keeping this in mind, right, we captured the using DSO, we captured the transient portion of the phase winding. Look at this is the time taken by the machine to reach its maximum value. So we captured this transient period. Tau is equal to L by R. Sorry, tau is equal to L by R. The resistance of the winding, right? And as I said, this time also, from this, you can calculate the inductance 5 times tau. Okay, using this, you can find out the inductance of the circuit. You can find out the inductance of the circuit. So this is how we calculated the aligned inductance. There are many techniques are presented in the literature. You can go through. I found it is very simple, so I can use this and we matched it. Right, we have got the correct value. So this is one of the thing. Just to explain this, I use the existing machine with me and I have explained it. And for the one which we have calculated the tractive force, which is under fabrication, probably I can show you experimental setup later. Okay, so the conclusion is radial force of SRM, so geometry based structural modification can reduce the radial force. Okay. And just I have listed some of the area at which you can concentrate. Probably most of you might have completed your research. Just I'm sharing. These are the some of the domains in which you can concentrate to carry out your research. Right? Optimal sizing and design of battery packs, which is many researchers are concentrating. Autonomous and connected vehicle, health monitoring, battery management. As of now we have no battery management system. We are uh, importing from some other countries and we are just fabricating all the components to develop electric vehicle. And the security is most important. Whenever you are connecting your electric vehicle with the grid, no one should steal the information. The security is most important. Fault analysis, you can work on it. Charging station on IoT platform, and as I said, vehicle to grid to vehicle capability, because most of the time your electric vehicle is going to sit ideally. In that time you can connect the battery power to the grid, or you can connect your battery. So this interaction between grid and vehicle can takes place. For that, yeah, as I said, we have to use pure electric vehicle or plug-in hybrid electric vehicle. Only then this grid integration is possible. And noise, vibration, harshness analysis. Whenever you design a machine, this noise, vibration, harshness analysis has to be carried out using, experimental setup, as well as many tools are there. Powertrain architecture, just now we discussed. So these are some of the domains which you can concentrate if you want to do research, or if you have done research to enhance our knowledge, we can concentrate all these things. These are some of the references. Okay. I just shared, whatever we have done. I just shared my own understanding. Something may be wrong. Please excuse me. If you have, anything to share with me, or any feedback or any questions, we can have it. And thank you very much for joining the session, because I know it's a late evening. It's very difficult for you to join the session. I thank you all once again for the patient listening, and once again I thank the organizers for providing me this opportunity. Thank you very much. Let me hear from you.
Thank you, sir. Participants, you can ask your queries. Participants, you can ask your queries.
Someone posted that, how to calculate radial force. See, in the advanced version, actually it is available. You can do it. There is a separate package is available in the magnetic. We can get it. Just as similar, you can get it. Not an issue.
Participants, if you have any queries, you can post it in the chat box.
Probably I might be little faster, it seems, because since I want to to give more information, I just I rushed up, actually, nothing else. Ma'am, you could follow, right, whatever I was talking?
Yes,
Yeah,
sir.
yeah, sir. It was excellent, sir. We were able to follow, sir. No issues.
Thank you, sir. Thank you very much.
Sir,
Yes, ma'am. Yes, ma'am.
Ashish sir has asked various torque populations control methods.
See, as far as torque is concerned, see, actually, torque control is a current control. Torque control is a current control. If you want to control the torque, the immediate operating variable which controls torque is the current. The current has to be controlled. To control the current, you can prefer the PWM technique. Because since you are going to, whether it is an induction machine or some other special electrical machine, certainly in an electrical vehicle, to have a control, it is operated by means of front end converter. It has got more power electronic switches which are triggered at some frequency. By adjusting the duty ratio, you can have the variation in the current which is flowing through the winding. In that, by using this current control, we can control the torque. Torque means current control, ma'am.
Okay. Sir, Mr. Shantakumar has asked, what is NHV? Can you please explain, sir?
Noise, vibration, harshness analysis, ma'am. That's what we are discussing right now, right? See, whenever the machine produces force, it can be divided into two components, like tangential force and radial force. Radial force is responsible for the vibration. Okay, what is the magnitude of the vibration? By means of this vibration, what does the noise produce? Doing all this analysis is called NVH analysis, noise, vibration, harshness analysis. How to reduce torque ripple in SRM using rotor and stator parameter. To reduce torque ripple, actually, the first thing is the pole configuration is most important. See, consider, we have got the different phases of machine: three-phase machine, four-phase machine. If we consider, we don't prefer three-phase machine, actually. Even for few applications, they're using it. That's different thing. Technically, if you want to understand, the four-phase machine has got more overlap. So the torque ripple due to four-phase machine is lesser than the three-phase machine. So if we increase the number of rotor poles, the torque ripple can be reduced.
Okay.
And
Okay, sir.
also we can have, variation in the pole arc optimization we can do to reduce the torque ripple. That is also possible. In the NFA itself, we can do pole arc optimization, ma'am. Sensitivity analysis we can do. அது பண்ணிட்டு நம்ம வந்துட்டு torque ripple minimization பண்ண முடியும். It is possible, ma'am.
Okay, sir.
Sir, may I request you to please provide your contact information in terms of email or so?
Sure, sir. I'll share with the Arul Prakash sir is in contact is in I'm communicating with Arul Prakash sir. I'll inform to you can get it from Arul Prakash sir.
Yes, sir. Thank you.
I'll share with you.
Yes, sir. Thank you.
Okay.
Sir,
Yes, ma'am.
Ms. Sarojini Harikrishnan has asked how to reduce torque ripple in SRM using rotor and stator parameters.
That is what, no, that's what I said. The number of rotor poles, number of phases, number of rotor poles is one of the major factor actually. If you increase the number of rotor pole arc, and as well as the rotor pole arc should be greater than the stator pole arc. Rotor pole arc should be greater than the stator pole arc. By optimizing the rotor pole arc, it is possible for us to reduce the. I am talking about the geometry modification. Okay, it's possible by having more number of rotor poles. It is possible.
Okay, sir. So the next question is from Prabhu Sundaramurthy. He is asked, which cloud platform is suitable for IoT-based condition monitoring, sir?
Ma'am, I'm not proficient in IoT actually. I may not answer this, ma'am. But we generally use this cloud for data sharing actually. I can tell you what is the role of IoT because in IoT, the data is accessed through cloud. So if you are using electric vehicle, the SOC of the battery should be shared in a cloud so that we can understand the range the existing SOC can cover, because the driver who's driving the vehicle should aware of the charging station which is available. Okay, so how long, what is the existing SOC, with that SOC how long we can drive. These things can be forecasted by sharing the data through cloud. Type of cloud I'm not proficient enough, man. I don't know actually. Cloud pati எனக்கு தெரியல.
Okay, sir. Thank you, sir.
Okay.
Vinod, sir.
Yeah, tell me, ma'am.
Vote of thanks பண்ணிடலாம்ல, sir?
If there is no any questions, then we can wind up for today's session, ma'am.
One more sir.
Which optimization technique is used for parameter optimization? Sir, in my FEA itself, we can do FEA by using electromagnetic tools itself. We can do FEA optimization. Otherwise, we have formula for everything. You have the formula for torque calculation, torque ripple calculation, average torque calculation, torque per unit volume calculation. Using these formulae, you can develop constraint. Use any optimization algorithm, whether it's a genetic algorithm or Wolf algorithm. Like this, day by day, many thousand number of algorithms are available. You can make use of any existing optimization algorithm using your own constraint. You can have a multi objective function. Cost function you have to derive. Probably considering all these factors is very difficult to optimize. You can consider any two factors. You can have weighting factors as W1, W2. By considering the torque ripple and the torque per unit volume, you can consider efficiency and torque ripple, you can consider. So consider formulate an objective function using minimum constraints. Say you can have two, using the existing formula in the literature, and then make use of any optimization method. There are n number of optimization methods are available, and before using the optimization, ensure that, because for all the optimization methods the algorithm is already available in a net. You can make very well, you can make use of it, but analytical calculation is most important. You do analytical calculation and verify.
Okay,
Yes, ma'am.
good evening, sir. Myself, Shinoy.
Yes, sir.
Actually, sir, you are saying that we can reduce the vibration by putting some windows on the rotor, sir. Whether
That
the
is-
shape of the window matters, or is there any criteria to choose windows, whether we can put in stator? Is it
No,
effective?
not randomly, not randomly. That's what I'm saying. Actually, the concept behind this is, the this I was talking about sound waves, right? The speed of the sound wave, propagates through solid at a faster rate, whereas the speed of the sound waves propagates at a lesser speed through the air and liquid. That is why we preferred windows. Okay, windows should be provided. There should not be any mechanical unbalance. There should not be any mechanical unbalance. There should not be any core saturation, right? So developing, formulating constraint is most important. See, not only this window, I just suggested window. Even you can go for skewing. Even you can go for skewing of rotor poles, skewing of stator pole alone, skewing of stator and rotor pole together. Okay, instead of having rectangular windows, you can have some other shape of windows. See to that the mechanical structure, the robustness of the rotor should not get reduced, right? And it is not advisable to have windows in the stator, because already due to crowding of flux lines there is a saturation. So we didn't prefer to have windows in the stator poles. That is why we placed it in the rotor poles, sir.
Okay, sir. Thank you.
Okay. Can you share some suggestion for converter selection? That's what I said. We have certain constraints while selecting the converter. See, the SRM itself has a highly fault tolerant capability. So the converters that you are using to excite the stator phase winding of SRM should have high fault tolerant capability, right? It should provide path for the demagnetization of the winding, as well as the demagnetized power should be utilized in a productive way by feeding power back to the source. So by considering all these factors, we have to choose the power converter, appropriate power converter. According to the survey, asymmetrical off-bridge converter is the best power converter to operate the SRM in a satisfactory manner.
Dear participants, for tomorrow participant will be resource person will be Dr. M. Prabhakar. So he will deal with more with converters.
Okay, sir.
Ma'am, if there is no question, we can wind up, ma'am.
Okay, sir. Okay, sir. Thank you, sir, for the wonderful session. It was indeed an in-depth session in the SRM-based electric powertrain for electric vehicle application. Today's session was a very interactive and lively session. You provided more insights about the difference between mechanical and electrical powertrains, problems associated with electrical motors, the calculation of tractive effort with an example of e-rickshaw, finite element analysis, flux patterns of SRM, transient analysis of SRM and its various modes of application. And also you gave an idea in the areas of research in e-vehicle. Thank you so much, sir, for the detailed explanation. Thank you, sir. I express my sincere gratitude to our Dean Ma'am, Dr. V. Jamana Ma'am, for joining with us and motivating us. I thank our beloved HOD, Dr. S.VINOD sir, for providing this wonderful platform. I extend my thanks to all the faculty members of EEE department. And at last, I thank all the participants for your patience. Thank you. Thank you, one and all.
Thank you all. Thank you all. Okay.
Thank you, sir. Thank you for accepting our invitation and sharing your valuable time, sir. Thank you, sir.
Thank you, sir. Thank you very much. It's my pleasure, sir. Thank you very much for providing me an opportunity. Thank you, sir.
Thank you, sir.
Thank
Thank you for your presence, sir.
Hey, sir. Thank you very much. We shall leave then, right?
Yeah, sir, we can.
Thank you.
Thank you, sir.
Participants, kindly fill in the feedback form.
Yeah, yesterday's video is being posted in YouTube, so you can even go through. And today's session will also be posted. Okay, sir. Thank you, sir. Arul Prakash, sir. I'm leaving.
Thank you, sir.
Thank you, ma'am.
Thank you, sir. Thank you.
Arul, sir.
Yes, ma'am. Tell me, ma'am.
Shall I stop recording, sir?
Ah, yes, ma'am. You can stop.
Okay, sir.